Okay, so today we're going to discuss here shows. This is the third method for the extraction metal. Okay, this time we heat the metal oxide, but this time alone is not enough to break the strong bonding. So this time we introduce something called reducing agents. Okay, now forget what is meant by reducing agent at this moment. First, we need to focus what type of metal oxide can be used or can be extracted by this method. Is the first one is copper 2 oxide, lead 2 oxide, iron 2 or iron 3 oxide, and zinc oxide. Okay, all these 5 or 4 elements, their compounds, their elements should be extracted by this method. Okay, and we need to heat the ore along with something more. We can have carbon or carbon monoxide or hydrogen. Okay, now as we mentioned before, first we need to memorize the work equation first. Okay, the work equation indicates first, how about heat the metal ore with carbon, and during the reactions they will form metal and carbon dioxide. So let's see. Here shows if we choose zinc oxide as an example, then we get zinc, of course, and CO2 according to the work equations. Okay, so here shows, of course, zinc is a solid and CO2 is a gas, but now you try to balance the equation. For the oxygen, we have 2 oxygen on the right hand side, so we need 2 zinc oxide on the left hand side, right? Then as we have 2 zinc oxide on the left hand side, we have 2 zinc metal in the right hand side. Okay, like this. Then we balance the equation with similar ideas. Okay, for the lead and copper, we can do the same with the same coefficients. Okay, so we try it down like this. Okay, and the result is 2, 2, 2, 2. Okay, so how about the iron metal? So as mentioned in the work equation, iron metal and CO2 should be obtained, right? Okay, this is all from the work equations. Then let's see. On the left hand side, we got 3 oxygen, but on the right hand side we got 2. So what should we do is we try to get the LCM or minimum multiple, and here shows we choose 2 here. Okay, that means on the left hand side we got 6 oxygen, and on the right hand side we need 3 CO2 to balance the number of O first. Okay, then we concern about the number of iron. Okay, on the left hand side this is 2 times 2, that is 4 iron. Okay, and finally on the right hand side, because we have 3 CO2, so on the left hand side we should have 3 carbon used. Okay, so this is the first point. And here shows the picture how the reaction undergoes in the laboratory. So you can see, okay, first this picture is important, so make sure you can write down or draw the experimental setup. And here we have a mixture of metal ore and carbon, then just simply heat it, it's okay. The second one is heated with carbon monoxide. Okay, now the work equation is like this, similar to that. With heated with carbon, we get CO2 and metal formed. Okay, with this idea, okay, first again we copy everything down. Okay, and of course the physical state, oh, sorry, not gas. Okay, now for the physical state, in case it is requested from the equation, you must write it, okay, otherwise you can forget it. And you can see here for the 1, 3 and 4, well done, we have finished balance already, right? Very simple. But for the question 2, let's see. Okay, on the left hand side, okay, we get Fe2O3, and you can know that each carbon monoxide can take away only 1 oxygen from the ore, right? So in case you have 3 oxygen here, that means you need 3 CO to take away all the oxygen, okay? And then of course you get 3 CO2. Understand? Then now we have finished balancing the number of O. Then we have 2 iron metal on the left hand side, so we should form 2 metal also, right? And we finish. But what I want to say is how the experimental setup shown here. First, we have carbon monoxide supply. So where the carbon monoxide comes from is from tank gas. Okay, from tank gas. And here we have a boring tube, and the metal oxide is placed in the middle with heating just below. Okay, then there is an opening. Okay, so be careful. There is an opening because if we keep pumping the tank gas, so there should be an exit for the tube. Otherwise, the tube will break due to the pressure, right? And don't forget to burn away the excess carbon monoxide. Otherwise, there will be fire hazard because carbon monoxide is flammable. Okay, we must burn off the unreacted carbon monoxide. Okay. Well, finally, we get reaction between metal ore and hydrogen. Here shows, but you need to be careful. This method is not suitable or cannot use it to extract zinc oxide. I will tell you later why. Okay. So again, don't forget the equation, and unlike carbon or carbon monoxide, this time no carbon dioxide is formed. We only have water. Okay. So here shows the copper become copper metal, lead metal, and iron metal. And don't forget we have water formation along. Okay. So again, the physical state and here. Okay. Let's see. Okay. Again, 1 and 2, well done. We finished already, right? Balancing everything. And for the third one, okay, this time each hydrogen can take away 1 oxygen. Now here we have 3 oxygen. That means we need 3 hydrogen gas, right? Then we need 3 here because 3 water molecule is formed, and don't forget add 2 here to balance the number of iron. Okay, very well. This time the setup, okay, is need to memorize how to draw it, but we replace it with hydrogen supply. It's okay. Okay, it's okay because the same setup as carbon monoxide. And again, don't forget to burn off the excess hydrogen. Okay. Now, so the extraction method for this type of metal, zinc, iron, lead, and copper, all these 4 metals should be used, okay, to heat the ore with something, okay, for example, carbon monoxide or hydrogen. But I want to say is, okay, among all these 4 elements, okay, we want to compare which one is more reactive. Oops. Which one is more reactive? Okay, from these 2 reactions, heat with carbon and heat with carbon monoxide, we cannot compare because all of them will break down under the heating with carbon and carbon monoxide. We cannot compare, okay? But this hydrogen reaction may give us some insight, okay? Now you can see, back to this idea, back to our previous idea, the element and compound, right? So we have mentioned if the element is stable, that means the compound is unstable. Unstable means, okay, they will be break down easily. Okay, they will break down easily. That is mean unstable. So let's see. For the copper, lead, and iron, okay, they will break down easily. That means their compound is unstable, right? The interpretation is like this. For the copper, lead, and iron, under hydrogen, they will break down. That means they are unstable, or we can say they are stable elements. But zinc, okay, but zinc is different, okay, because hydrogen cannot break down zinc, okay. That means compared with zinc, hydrogen is less attractive, right? If hydrogen is so attractive to oxygen, then zinc oxide will break. But now, no reaction, no breaking, no decomposition means iron or zinc oxide is quite stable. Okay, quite stable. Or that means their element, the zinc element, is quite unstable, or we can say zinc metal is more reactive than the others. Okay, so here zinc metal is reactive and the rest of them is less reactive. Okay, we use this method to compare the reactivity among these 4 elements. Okay, so I want you to get the idea how can we compare the reactivity. Okay, so if no problem, then we go further. Okay, here is the laboratory setup for extraction. So how about the industrial setup? The industrial setup is something like this. We have something called blast furnace. Okay, you just know the name is okay. No need to memorize. Okay. Now first, inside the furnace, we mix the iron ore and coke. Okay, now coke is not a soft drink. Okay, coke is a kind of carbon and limestone. Okay, here shows the limestone is used to remove the impurity first. Okay, the second idea is limestone is added to the mixture as impurity to lower the melting point of the ore. Okay, because if melting point exists, if impurity exists, then the melting point will drop. You have this idea already. Here shows, right? The impurity can be used to lower the melting point. Okay. Well, next. So the inside there, involve 2 steps. The first step is the carbon combined with oxygen to form carbon monoxide. And the second one is the carbon monoxide combined with iron ore to form carbon dioxide and iron. Okay, now here shows why we should use carbon monoxide instead of carbon powder to react with iron ore. Okay, so in the purity section, you can see both carbon powder and carbon monoxide can extract iron. So why we should spend time to form carbon monoxide first? Okay, why we do not let the carbon powder react with the ore directly? Okay, now this is because there are two considerations. First, the reaction or the extraction need high temperature. So step one is actually burning carbon, right? Step one is burning carbon. So step one will give out heat energy for the high temperature environment. This is the first point, okay? We need to generate heat energy, okay? The second one is because if we use carbon directly, okay, don't forget carbon is actually a solid, okay, and they will mix with the iron metal. This is difficult for us to separate, okay. Further separation means more money should be involved, so we should use carbon monoxide, which is better for the further purification, okay. So if you have any problem, feel free to ask me later on.